And it's an honour to be able to present. I'm sorry I couldn't get there in person, but as you know, the border is closed and I'm stuck at home in Melbourne. I've been in this room for far too long, but at least we can visit virtually. So I'm going to talk about some recent work I've been doing on forecast reconciliation. Before I do that, before I tell you about what I'm going to talk about in particular, I thought I'd motivate it by an example of Australian tourism data. So this is Australia obviously divided into states, and then the states are divided into smaller zones and then into regions. And we have monthly data on the number of visitor nights. So that's the number of nights that people stay in each region when they're not residents there, between 1998 and 2017. So this is a national survey that's done. We have interviews with 120,000 Australians aged 15 plus over that period. And as I said, it's split into states and then into zones and then into regions. And we're interested in forecasting at all the different levels. We want to forecast the regional number of tourists, the zones and the states. And this is an ongoing project. My colleague, Georgia Thanasopoulos, and I are currently working with Tourism Australia to try to forecast the next year or two. And as you can imagine, that's quite a challenging thing to be doing at the moment because the tourism numbers have dropped a lot. But I'm only going to deal with the data up to 2017, so we're not having to think about COVID-19 here. So if you're in R and you look at the data, it looks like this. There's a month column, then the state, the zone, the region, and then the number of visitors. And so there's quite a lot of data. There's 18,000 rows here. And there's 75 unique combinations of state, zone and region. And that's what that 75 there means. So just to show you what the data looks like, this is total domestic travel in Australia. So this is adding up across all the regions, and you can see there's quite strong seasonality with sort of unusual peaks during the year, depending on where people want to travel. So they tend to be traveling to the snow regions in winter, obviously. They're traveling to the southern regions, places like Tasmania in summer and so on. So you end up with this sort of unusual pattern. You've got some trend as well, particularly over the last 6 or 7 years. If you drill down to look at the, this is before I look at the states, this is looking at the seasonal pattern over a year. So this is exactly the same data set, but instead of plotted against time, it's plotted against a month and then wrapped around. So each year consists of one line on this plot, and you can see that the peak tends to be in January, and you get smaller peaks in April and July and October. If I drill down to the states, and I'm doing this on a log scale because the states are of such different sizes, New South Wales is up there at the top with a similar seasonal pattern to Victoria. But if you look down, you'll see, for example, the Northern Territory has a very different seasonal pattern. It has a trough over summer instead of a peak. And so it's out of sync with some of the other states. And there's less seasonality in Western Australia and in South Australia. You can drill down further. Now we're down to just one zone. So this is, one state. This is New South Wales by zone. And you can see it's getting noisier as you drill down into the more disaggregated data. And we can go down to region, and you can see it's even noisier. This is one region within New South Wales. And it's pretty noisy with a lot less signal than you see at the higher levels of aggregation. Okay, so what we've got here is a hierarchical time series. It's a collection of time series that are linked together in this hierarchical structure. In the example that I've just showed you, the hierarchy is formed by the geography of the geographical nature of the data. So you've got the totals, we've got states, we've got zones, and in the data I showed you, we had another level, which is regions. But you could also imagine data that has some non-hierarchical grouping structure. So here's a little example with 4 disaggregated series, and they can be grouped in 2 different ways. So if I add AX and AY together, I get A. If I add BX and BY together, I get B. But if I add AX and BX together, I get X, and so on. So this sort of thing would arise if I had tourism data by state and by purpose of travel. So there's not a natural ordering of those two factors. So I could split by state and then by purpose of travel, or I could split by purpose of travel and then by state. It also arises in retail sales where you've got product groups as well as geography, and the product groups can disaggregate into subgroups right down to packet sizes. And here's the geographical hierarchy, countries, regions, right down to store level. So you get these two different hierarchies that get crossed together. So you can have quite complicated grouping structures. Okay, so that's sort of the problem, is dealing with data that looks like that and trying to generate forecasts for all of the different levels in a way that they add up appropriately. So we call those coherent forecasts. So a coherent forecast is where you've got forecasts of aggregates and disaggregates, and the aggregated forecasts are equal to the sum of the disaggregated forecasts. And the aggregation structure can be complicated, as I've just explained. So up until 2009, there was really only three ways discussed to do this. There was what was called bottom-up forecasting, where you forecast all of the series at the bottom level, the most disaggregated series, and you added them up. There were a few different ways of doing top-down forecasting, where you forecast the most aggregated series, and then you disaggregated those forecasts down the tree. And then some businesses were doing what they called middle-out forecasting, where they pick a level in the middle of the hierarchy and they'd do bottom-up from that level up, and they'd do top-down from that level down. So up until 2009, these were the only methods that were in existence, and any academic literature that talked about this problem was talking about which method should you use in which problem. I had come across this quite a lot in my consulting work and back into the late 90s, and always thought there's got to be a better way, a more statistical way, a more sort of objective way of trying to do this. And so that's where the idea of forecast reconciliation came from. The idea is you forecast all of the series at all of the levels, ignoring the aggregation constraints. So obviously when you're forecasting this number of series, you have to do something automatic. You can't build separate models by hand. So we applied things like ETS forecasting or ARIMA forecasting, which are automated algorithms applied to univariate time series to generate forecasts. And then once you've got those forecasts, which will not be coherent, they won't add up because you'll have different models applied to different nodes in the hierarchy. Once you've got those forecasts, we then reconcile them so they are coherent. So we adjust them using a least squares optimization approach. That is, we find the closest reconciled forecasts to the original forecasts. So we call this reconciliation, and there's been quite a few papers on it since 2009. So I'm going to talk about this stream of papers, which form sort of the, at least some of these are now the seminal papers in the area. You'll notice there's an unusual ordering here. The first one, which is the first methodological paper that we wrote on it, came out in 2011, even though an application of the methodology came out in 2009 that shows how long it took to get that first paper published. Lesson is, if you're going to do something very different from what everyone else is doing in the literature, it sometimes can be hard to convince referees that it's a good idea. Lesson 2 from that is we actually made quite a few mistakes in that paper. The referees picked up some of them, which is one of the reasons it took a few years to get out. But some of the other errors in the paper we didn't realise until later, and some of these subsequent papers sort of fix up things that we'd done in the earlier ones. But you can see the main names associated with this line of research. Apart from me, George Athanasopoulos appears in all but one of these papers. In the later ones, Anastasios Panagiotoulis and Pawasala Gamakamara appear there. And another key contributor here is Shanika Wickramasuriya. I specialise in co-authoring with people with long names. Another name you might recognise is Shang here in the very first paper. That's Han-Lin Shang, who is of course now at Macquarie. Okay, so let me now introduce some notation so we can do some mathematics on this problem. So suppose this is my hierarchy. I'm going to a very, very small hierarchy to begin with. It has a total that consists of 3 series. I can write the data associated with this series like this. A vector y consisting of 4 components. Yt is the total series at time t, and y, a, b, and c are the series in these nodes at time t. This red vector b is the bottom level series. So that's just the series at the most disaggregated level. And this matrix S is a summing matrix, S for summing, and it gives you a way of taking the bottom level series and constructing them into the top level series. In this case, it's trivial. In other cases, it won't be quite so trivial. Okay, so boldface Y is all the data. Boldface B is a vector of the most disaggregated series. S is the summing matrix, and we can write it as Y equals S times B. And in fact, every one of these problems can be written in that form. Just to show you a couple of examples, suppose I had 3 levels, then Y is equal to S times B would look like that, where I've got the second level, the sort of intermediate level as my, after the top series, I've got the next 3, and then the bottom series given here. And so the bottom part of this matrix is an identity, and then I've got this block structure in the middle part and a row of 1s in the top part. If I took this particular construction where I've got 4 bottom level series, I'm interested in the row totals and the column totals, as well as the overall total. I can also write that using the same notation, Y equals SB. And as I said, any kind of aggregation structure at all, including sort of complicated nesting and crossing problems, can be written like this. Okay, so that's the basic notation. Now let me introduce a little bit of geometry to describe what's going on here. So here I've just got 3 series. I've got an A and a B series and a total. Okay, so we've only got an even simpler hierarchy than the one I showed you on the previous slide. Because the total must be the sum of A and B, the values on the y-axis, on the vertical axis, have to be on this plane, this subspace on the 3D, in the 3D space. So that's called the coherent subspace, and it's the space where the constraints will hold. So a hierarchical time series is a time series that lives on this space. Now, normally we're talking about much higher dimensional space, sometimes in the millions of dimensions in some of the consulting problems I've done around this work. But you can think of it as a multivariate time series that lives on a subspace within the larger n-dimensional space. And a coherent point forecast is a point forecast that lives on this space. So it adds up in the same way that the data adds up. There's 2 reasons to want to create coherent point forecasts. The first one is that they're generally more accurate, and I'll show you, I'll quantify that more carefully later, but you'll generally get better point forecasts if they live on the coherent subspace. The second reason is you often use these forecasts for a reason, and then having them add up is important. For example, an organisation may allocate budget to divisions of the company and then to subdivisions of the company based on the forecast activity for the next year. And so obviously they have to add up because they have to somehow divide the available money up appropriately. If I just did forecasting and ignored all of these constraints, I just forecast all of the different series at all of the different levels, I get what's called incoherent forecast. I'm going to call that y hat. And then my reconcile forecasts, where I map them onto the subspace, I'm going to call that y tilde. Now, I want to do this because I get better forecasts at the top level if I actually forecast that directly, and I get sometimes get better forecasts at the bottom level if I forecast those directly, but I want them to add up. So I want to do all of this forecasting on all of the different levels and then add them up, make sure they add up appropriately by reconciling them using this map. So this psi map maps from the big space down to the subspace. Okay, so y tilde is a mapping of y hat via this psi function, which we have to define. Okay, so far, almost all of the available reconciliation approaches are linear. That is, they create a linear function from the n-dimensional space down to the subspace. So a way of characterizing linear reconciliation methods is you write them like this. It's S times some matrix G times Y hat. And if you think about it, every linear mapping has to work like that because G will extract and combine the original forecast to get forecasts for the most disaggregated series, which we call bottom level forecasts. And then S will add those up again onto the subspace. So you've got both a extraction down to the disaggregated level and then an expansion back up to the aggregated level, but you do it in such a way that you end up with coherent forecasts through this S times G linear function. The very first one we came up with to do this was we called OLS reconciliation because it looks like ordinary least squares. And in fact, we derived it using a regression. I'm not going to talk about the regression sort of interpretation of this problem today because we've subsequently decided it's better to think about it as an optimization problem rather than a regression problem. But the formula, whichever way you look at it, it looks like this. So G is S prime S inverse S times S prime. And geometrically, since this is a talk about geometry, you can think of it like this. This is a schematic only because you need at least 3 dimensions to talk about reconciliation. And I'm doing this in 2 dimensions. But you can think if the subspace, the coherent subspace is this this arrow here S, then my thing that I'm trying to forecast, the data will lie on that because the data is always coherent by definition. The forecast that I come up with using models for the different series will not necessarily lie on that subspace because I'm using different models for different series. So it's going to lie up here off the subspace, Y hat. And reconciliation is going to map from there down onto the subspace, and a projection, orthogonal projection, will map down there like that so that it's orthogonally mapped onto the subspace. But other projections will also map linearly from here down to here. So if SG, this linear reconciliation function, is a projection, then there's 2 things come out of that. Firstly, that if I already have something that's coherent, then it doesn't move, it stays exactly where it is. And if I have something that's unbiased, but incoherent, then it remains unbiased when it is mapped onto the coherent subspace. We have a proof of that in one of the papers that I referenced earlier. And the orthogonal projection like this leads to the smallest possible adjustments of the base forecasts. Not necessarily the best reconciliation, but the smallest possible adjustments of the base forecast. So that came out of our 2011 work and was sort of the first attempt at doing reconciliation. In that 2011 work, though, we didn't have a geometric interpretation. It was, as I said, derived from a regression perspective. One of the things that has come out of this work is that we have this nice distance reducing property, that if you have an orthogonal projection, then you're guaranteed that this particular measure of accuracy will improve as a result. You will get better forecasts. This is an L2 norm, and I'm talking about a Euclidean projection, so a very specific norm and a very specific way of measuring forecast accuracy. But this is a pretty remarkable result because it holds for any realization and any forecast. You are guaranteed by doing this to get a better forecast under this measure of accuracy. And you haven't added any more information. You've just taken the information you already know, but you've improved your forecast through this projection. However, so that sounds fantastic, but it's not necessarily all it might appear, because other measures of forecast accuracy may be worse. Individual forecasts may be worse, even though overall, applied to the whole vector of forecasts, things are guaranteed to get better. And it's not necessarily even the best reconciliation approach to minimize even this particular measure of accuracy. but it does give you some sort of interesting property. There's no assumptions here about where the base forecast came from, where the how the data is generated or anything. It's simply a result of orthogonal projections, essentially Pythagoras theorem. Okay, so that's just the same formula up again. The reconciled forecasts are this projection, S times G of the base forecasts. Now, come forward to the JASA paper that was published in 2019, and it contained this result, which we call MINT reconciliation. This is a slight reinterpretation of it based on the geometrical interpretation, but if SG is a projection, then the trace of the variance of the reconciled forecast is minimized under this value of G. So if V here is the variance of the reconciled forecasts and W is the variance of the original base forecasts, then you can minimize the variance of the new forecasts by applying this, this G. So it gives you an optimal reconciliation. The W is the variance of the base forecasts. Okay, that's sort of a pretty cool result due to one of my PhD students, Shanika Wickrama-Surya. So if you think about what's going on here geometrically, we think about our big space, the original space that the forecasts lie on. This is meant to represent the direction of deviations from the coherent space. So R is the direction of the largest deviations from the coherent space. And I'm interested in projecting my forecast onto this space. So if my grey spots here are now base forecasts, or the potential base forecasts I could get using different approaches, the actual unknown Y is this black dot here. The forecast that I happen to have produced is the blue dot, but I could have produced one of these other ones. Then if I just use orthogonal projections, ordinary least squares reconciliation, I'm projecting these grey dots onto this subspace orthogonally. So I'm projecting straight down. And so the red shows you, gives you some idea of the variance of those reconciled forecasts. If I do it obliquely, I get this approach. So this is what you're getting from MINT compared to OLS. You're projecting obliquely along the direction of greatest variation. And then you can see the red line is much shorter. I'm getting smaller variance in my reconciled forecast as a result. So this is sort of a geometric explanation of this MINT reconciliation. Okay, so there's a bunch of reconciliation methods. I talked about OLS and I talked about the MINT. What I didn't talk about back here is, well, how do we estimate this W? That's actually not that easy to estimate. So there's some approximations we can use. We could just worry about the diagonals of that matrix and ignore the off diagonals. That gives us WLS. Or we could try and estimate it using this approximation. If we estimate it using this approximation, assuming that the 8-step ahead forecast covariance matrix is proportional to the 1-step ahead forecast variance matrix, and then using some kind of covariance estimator, we get a couple of different types of MINT estimators, which we call MINT sample and MINT shrink. So MINT shrink works substantially better, especially for large problems. We're shrinking the sample covariance estimator down onto the diagonal. So all the off diagonals get shrunk a little bit. Okay, so that's forecast reconciliation using using the geometry to explain what's going on. So the algebra was known, well, the OLS part in 2011, the MINT part in 2019. The geometric interpretation is new. That's just about to come out in the International Journal of Forecasting. One of the nice things about thinking about this geometrically is it also allows you to think about, well, how do you reconcile forecasts that are distributions and not just point forecasts? And usually you don't just want, you know, point forecast numbers, you want a whole distribution. So let me talk a little bit about that problem. So we can take the same idea of projecting onto the subspace, but now we're going to be projecting distributions and not just points in that space. So firstly, we need to define what coherent means even in a large space like this. So it's easy to define coherence for point forecasts. Things have to add up. The lower level has to add up to the upper level. When you've got a distribution that sits you know, these in this space, what do you mean by coherence? So our first attempt at defining that, we defined it in terms of convolutions because you're summing distributions up. So a convolution sort of seems a natural thing to do. But in fact, it turns out to be better to define it in terms of projections in space. Given the probability triple, where F is the usual Borel sigma algebra, then we can think of the original base forecasts as a probability triple in the original space, and a coherent one is a probability triple in the subspace, where we've mapped from the original space down onto the subspace. So we have a mapping that maps the original thing down onto the bottom level forecasts and then extracting back up to the subspace. And then a probabilistic forecast reconciliation is then simply this, given by this definition. It's a natural extension of point forecast reconciliation. It transforms an incoherent probabilistic forecast into a coherent probabilistic forecast. The same probabilities are under the two sets here. When you do the mapping, you preserve probability space, but you ensure that you satisfy the constraints. Okay, so that's the definition then. And then if we then apply that to using our linear projection approach, we can derive the density of the bottom level series and then the density of the whole of the coherent space. So here we are taking G with a little minus superscript, means the generalized inverse. G perp here, this symbol here, is the orthogonal complement to G. And from those two, we construct G star. And then we take the determinant of that and we integrate out from the base forecast distributions like so. And then we can find the reconciled density under the full hierarchy. Okay, so there's a bit of theory here to get this, but it gives us a distribution. And then the nice thing is, under some distributional assumptions, some really nice results fall out. So if the incoherent base forecasts are normal, then the reconciled density is normal. We also have some nice results for elliptical distributions. If the incoherent base forecasts are elliptical, then the reconciled forecasts are elliptical, and we have some results on what they look like in the most recent paper that I listed before. Okay, another nice thing that comes out of this definition is this result, which is super practical. So if you have a sample that you draw from the original incoherent probability measure, then you can reconcile the samples using MINT or whatever else, and you will get samples on the reconciled probability measure. Okay, so even if you don't want to assume anything about the distribution, you just want to generate from some bootstrapping approach, you can then simply reconcile the sample paths and you will end up with something that's correct in the coherent subspace sense. Okay, so a really useful result for practical non-parametric simulation in this area. Okay, how are we going for time? Okay, so I'm going to talk a little bit about what are we going to do with these results now. So the sort of the hard mathematical bits are done. I'm going to now talk about, well, how do we know whether what we've got is any good? So let me go back to talk about this particular problem, and I'm only going to talk about one series and how do you decide whether your probability density is a good forecast for this series. And then I'll talk about how do you scale it up to the whole hierarchy. So suppose I just had this single series, which is Australian domestic tourism monthly data over about 20 years or so. So I fit a model. I might fit an ARIMA model. I generate future sample paths from my ARIMA model, and I get possible future sample paths that look like this. Okay, I'll do this lots of times. So I just zoom in on that last bit to make it easier to see. But I've fitted a model to the longer data set, and I've fitted an ARIMA model. I'm generating future sample paths. They're going to show the uncertainty in my future distributions. So I do this a lot, and I end up with a lot of sample paths, thousands of them. And then from those, I can compute the distributions. I'm doing it this way so you can sort of get an idea of where the distributions come from. In practice, we often derive these analytically, but if you were using a simulation approach, this is how you would do it. We can then estimate distributions by looking at each point in the forecast period, and for all of the simulated paths that pass through that point, you can then find the quantiles of that distribution empirically. So that gives us these deciles. So the middle one is the median, and then the others give you some idea of the uncertainty associated with your forecast distribution. Okay, so, and then I've got what actually happened. So this is forecasts. I trained my data up till the end of 2017, and I'm forecasting 2017 through to the end of 2017. So I've got what actually happened in black, and the idea is, well, how good is that? You know, the fact that it goes above the 90th percentile here and it drops down below the 30th percentile here is how do I measure how good that is? Okay, so we're going to use what's called quantile scores. So I've got the graph up here again, just the same graph you saw on the previous slide. My quantile forecasts are these blue lines. So they're the forecasts for different probability values at each time period. The Y is what I actually saw at each time. So that's the black line here. And then my score is the difference between them, but weighted by the probability. So Y minus Q is the absolute difference between the black line and any one of those blue lines. And then the weight out the front sort of weights it according to how likely it is to be above that line and how likely it is to be below. So if I've got P is 0.5, then it's equally likely to be above or below. So this 2 times 1 minus P becomes 1. This one becomes 1. So my score is actually just the absolute error. But if P was, say, 0.1, the bottom line here, then it's unlikely to get below that. So this part of it has a low weight, has a weight of 0.2, and the weight of it being above is twice 0.9, so 1.8. So it has a high weight for being up there, because if I get it up there, that's what you would expect. And so low is good, small number is good here. The 2 multiplier, which is usually omitted, if you read any literature on quantile scoring, they won't put that 2 in. I put it in for 2 reasons. One is it means that you can interpret these like they're absolute errors, which is nice when you're trying to explain it to a non-technical audience. And secondly, you can simply average them and you get continuous rank probability scores, which is a score of the whole distribution. And this animated graph here is just showing you what this function looks like for different values of P. Okay, so if I average this over all possible values of P, I will end up with a score of how good the whole distribution is, not just one quantile. Okay, so that's called CRPS, and here it is. That's the average across the score, average of the scores across all P. So just an integral of S with respect to P. F here is the forecast distribution. It turns out that that thing can be also written like this. The expected value of the difference between a draw from F and what you saw minus the expected value of 2 draws from F. Okay, so it's sort of an interesting result because it makes it easier to generalize this to other contexts. The other nice thing about CRPS is you can show that it's optimal when F is the truth. So if you actually nailed the true distribution, or somehow you found out what the true distribution was, then you get this CRPS will be optimized, asymptotically, of course. That's what's called a proper score. Okay, so we can generalize this to a multivariate forecast by simply taking the second result and turning everything into vectors. There is another common multivariate forecast measure for probability scores called log score, which looks at minus the log of the density of the results. Now, we're not going to use that for a reason I'll show you shortly, but I wanted to just mention it because it's quite a common probability scoring method that's used in this space as well. Okay, so remember, a proper scoring method is one that's optimized when the true distribution is used. When you're comparing coherent with incoherent, that's not a proper measure if you're using log score, whereas the energy score is a proper measure. So that's why I want to use the energy score, because I want my score to be optimized when I get it right. If I'm comparing two different ways of doing coherent forecasting, so I might have two different types of projections, for example, then energy score, I need to use all of the hierarchy. I can't just do it on the bottom level, because if I just did it on the bottom level, I may not get the right ordering. I might choose to use one type of projection rather than another, whereas if I did it on all of the hierarchy, I would get the right ranking. So rankings can change if you don't use it. So the recommendation is use energy scores and reconcile, so measure the whole hierarchy. And in fact, I haven't got time to talk about this, but we have an algorithm for optimizing, for choosing the optimal projection, optimizing the energy score. And we have an R package to implement it. Okay, but I wanted to finish by just going through a couple of examples to show how this works in practice. So here's the Australian tourism data that I started with. So here is how to do it in practice, and it's really quite easy. This is using the Fable package. So first of all, you have to tell it, how do these data aggregate? The original data, you've got the various factors, states, zones, regions, and any other factors you might have. And you have to say, well, how do these, what aggregations are interesting? What aggregations are sort of meaningful here? So you set up an aggregate key, which describes how these key structures aggregate. And in this case, state is nesting zone, which is nesting region. So this / means nesting. If they're not nested, if they're just two factors that are not hierarchical, then you put a star in instead of a / to show that one's not nested with another. You're interested in the cross terms of those two factors. And then how do you combine the results? So summing is what we're normally doing, but you don't have to. You could have some other linear function instead. Okay, so once we take the aggregated data, notice I've stored that in Tourism Ag, and that looks like this. So there's quite a few more rows here because I've got all the aggregations I've added as well. And if the factor is aggregated, it just says aggregated. Right down the bottom of this table, you'll find all the original data non-aggregated, and you'll have rows where some things are aggregated and not other things. I'm going to take the data up until 2015. So I'm going to hold back 2016 and 2017, and I'm going to fit ETS models. So every possible row of every possible combination of the keys has a different model. So if I'm just modeling New South Wales, then the state is New South Wales, the zone and region are aggregated, I've fitted this model. For metropolitan New South Wales, I fitted this model, and so on. For metropolitan Sydney, I fitted this model. So it just shows you some of the models that have been fitted. There's 110 different models being fitted with this small bit of code. Then I take that thing, which I've saved as a thing called fit. I take that and I've then said, okay, let's now apply reconciliation. So I say I want to reconcile the results using minimum trace. So that's the MINT method applied to these models. And then I want to forecast 2 years ahead. I have to do the reconciliation step before the forecast step so that it can take account of all the, it can measure the correlation matrix of the residuals. If I put it after the forecast step, then it loses that information because it's trying to be efficient. So you put it first to say, I'm going to need reconciliation happening here. So go ahead and get that, whatever information you need. Then when I do the forecasting, it comes back with forecasts for both the original model, the ETS model, so they're the base forecasts, and the adjusted model. So it'll have both sets in here. As you can see, there's now 220 combinations instead of 110. And for each forecast, I have a distribution. So this is normal, certain mean and certain variance. And the mean is also extracted as a separate column. So it's all distributions are stored in there. Show you what some of them look like. So here is my, I'm just pulling out the results for when the state's been aggregated. So this is just the final total aggregation for the whole country. And I'm showing what the forecasts look like. So I've got the ETS is the in the red, the adjusted is in the sort of blue-green area here. As you can see, it's probably too tight. It's probably over. It's estimated the uncertainty to be too small. The black is the actual, and I can see how accurate it is. And I can do this for each of these things. So this is for New South Wales. This is for Melbourne. This is for the Snowy Mountains, and so on. So I can just pull out the individual series here. This one that doesn't make much difference whether I've reconciled or not. McDonnell Ranges, and so on. So then once I've done that, I want to then see, well, how well is my forecast doing? So I'm going to do a little bit more this time. This shows you the full workflow. I'm taking my aggregated data. I filter it to the end of 2015 for training purposes. I'm going to fit two models, an ETS model and an ARIMA model, automatically to each series. I'm also going to take the combination approach. So that's the average of the two forecasts. And this will take into account the correlations between them because it's going to do distributional forecasting. So all I have to do is to say I want to average them, and it'll do the convolution for me. I'm going to do minimum trace on all three models. I'm going to forecast 2 years ahead. And then I want to compute accuracy measures. I want to see, well, what's the CRPS? So it gives me a CRPS for each model and for each series. I've also asked for the skill score. So that is, well, what's my CRPS relative to a naive model? So relative to something really basic. I need to do that because the CRPS is all going to be on different scales. For the whole country, it's going to be much bigger than for a region with not much tourism. So I need to allow for that. So a skill score allows for it. This is a proportion change as a result of my model. And then I can just summarize the results and see what it does. So my ETS is the worst, and ARIMA is the best. The combination is between them. And notice the adjusting, the reconciliation improves every single time. So the adjusted ETS is better than ETS. The adjusted ARIMA is better than ARIMA. So the reconciliation helps improve my CRPS here. Okay, so that's an example of applying it to Australian tourism. I was going to also show you another example, but I think we've only got 10 minutes left and I need time for questions. So I'm going to skip that example and skip to the end. So I just wanted to acknowledge the many co-authors that have contributed to this work. More than these 7, but these are the 7 that co-authored the papers that I've particularly referred to in this talk. So my 2 colleagues, George Athanasopoulos and Anastasios Panagiotoulis. On the bottom row are the various PhD students and postdocs who worked on this. Hanlin Shang, of course, who's now a professor there at Macquarie. Shanika Wickramasinghe, who's now a lecturer at Auckland. Pawasala Gamakamara, who's now a postdoc with me. Iro Wang, who's now a lecturer at Auckland. And Mitch O'Hara-Wild, who's on the top row, is my main package developer. So he has done most of the work on the coding for this and written the Fable package. Iro Wang wrote the Sybil package, which underpins it. And together they have done an awesome job. So slides and papers available from my website. The package is available from tidyverts.org or from CRAN. There is a textbook which uses the Fable package. It doesn't yet include the chapter on reconciliation, but it will do in the next few weeks, I hope. You can find me at these at these places. And with that, I'll stop and take some questions. I'll just stop my screen here.
Yeah. Thank you very much, Rob. That was amazing result. Okay, anyone, you can unmute yourself and you can ask your question. Any question?
Yeah, so I have a question. Rob, you mentioned in your code examples nested and hierarchical variables. Can you clarify the difference between what is nested and what is hierarchical?
Yeah, so suppose with the tourism example, I had states, regions, zones, and purpose of travel. In fact, the data does have that. I just didn't show the purpose of travel in my example. So purpose of travel is not nested with the other regions, the other keys, because it doesn't naturally fall within states. So it's called a crossing factor, because I can look at the purpose of travel by state or by region or by zone. I can split just by purpose of travel and combine across all of the other keys. So it's not nested in that sense. So that's what I mean by crossing. And the syntax in the package allows you to have both nesting and crossing and combinations where you can nest some things and cross other things.
So when you mention crossing, that is the multiplication sign we use to it can either, so it's not a hierarchical variable. Treat it as a nested variable is what you're saying.
Yes, yeah, that's right.
Got it. Thank you.
Any other question? No question? I have my own question. Can we apply non-parametric method for forecasting in this problem?
So can you use your own method, did you mean?
Non-parametric method.
Yeah. So I was showing you a parametric method here because I was using ETS and ARIMA, which is both parametric models, and the probability distribution was normal. So that was also, so everything was fully parametric. You can also do it non-parametrically if you have a way of simulating sample paths from whatever model you're using. And you can with the software too. You just have to say bootstrap equals true, and instead of assuming a normal distribution, it will bootstrap the residuals and give you sample empirical distributions, which will then reconcile.
Okay, thank you.
So if I can ask one more question. I had a question in terms of interpretation. So for example, you mentioned multiple time series will have multiple models associated with it, and then we reconcile it. Say for example, the reconciled forecast doesn't have a model associated with it. How do you explain the result?
Yeah, so it can be even more complicated than that, because you can have very different models for different parts of the hierarchy. And so your reconciliation sort of combines all of the forecasts from whatever model they were generated from. So there's certainly no sort of generative model associated with the reconciled forecast. So when I'm working with clients, we just explain that this is the, sort of our estimate of the uncertainty, taking into account all of the information at all of the different series we've got. But you don't have a model that can you can look at terms in that model and interpret things. It's not about interpreting the results. It's about getting the best forecast you can.
Got it. Thank you.
We have still time for more questions. Okay. I think we don't have more questions at the moment. Okay, please join me to thank Rob for his great talk. Thank you very much, Tom.
Thank you.
Thank you. Have a lovely weekend.
Yeah, you too. Bye.
Bye-bye.